In this video, we'll have a look at our last few examples of integration by parts. Now in these examples, we're going to see what happens when we have a recurrence of our original integral. And you'll see what I mean by that as we get into the question. So here we're going to start off with the integral of sine of log of x. So this isn't sine times log x, it's sine of log x. So this actually lends quite well to the previous video when we were looking at what happens when we only have one function to integrate. And what we do is we look at this as the integral of 1 times sine of log x. So we've actually just now created that second function. And now we can go ahead and choose our u and our v dash. So clearly we need to be able to differentiate sine of log x, or that's what we need to choose to differentiate. Otherwise it would become redundant, because if we chose it as v dash, we'd be trying to integrate it, which is what the question is anyway. So differentiating this gives us, well, when we differentiate sine we get cos, but then we also have to multiply by the derivative of the inside function, which is the derivative of log x, which is 1 on x. And then our v dash is going to be 1, and v is going to be x. So now we can apply the integration by parts formula, which is u times v, so x times sine of log x, minus the integral of u dash times v. So that's going to be cos of log x times 1 on x, so that's u dash, and then we times by v, which is x. And you can see that this x and that x will cancel, and we'll be left here with the integral of cos of log x. And this is also going to require an application of integration by parts. So we're going to choose u to be cos of log x, which means that u dash is going to be minus sine of log x times 1 on x, or just divided by x. And then again v dash is 1 and v is x. So we can apply the integration by parts formula, and we get x sine of log x. Now we have a minus, so I recommend putting a large bracket here. U times v, so that's going to be x times cos of log x, minus the integral of u dash times v. Now u dash has a negative, so this negative and that negative will make it a positive. Sine of log x over x times x dx, and we close our brackets. Okay, let's tidy things up a little bit. So we have x sine of log x minus, now if we distribute that minus through, we'll get x cos of log x here, and then we'll also get minus this integral, but if we tidy it up we can cancel that x with that x, and so I'm left with the integral of sine of log x dx. Now this integral here is exactly what we started with. Okay, so the left-hand side is in fact that integral as well. So if I was to move, let's highlight this, if I was to move this integral to the other side, I would actually have 2 times that integral, because I'm adding that integral to itself. So this means that I actually have 2 times the integral of sine log x dx. That should be equal to x sine of log x minus x cos of log x. And now we can divide by 2 just to get the integral of sine x log x. So we have the integral of sine, I think I said sine x log x, I should have said sine of log x. So this integral is equal to 1/2 of everything on the right hand side. So 1/2 of x sine log x minus x cos log x. And since this is the end of our integral, and since it's indefinite, we need a plus c. Okay, and that is our final answer. The second example is the integral of e to the power x times sine x. Now here we do have two functions, so we don't have to multiply by 1. And both of these are actually quite easy to integrate. So what we choose as u and what we choose as v dash is actually not going to make a difference in this case. Now, before we start choosing our u and v dash, I might just write I equal to this integral, and you'll see why I'm going to do that. This is actually just something that's going to save a bit of time. And I think it's a good habit for every integral that you do to write let I be equal to the integral. Okay, so now let's go ahead and do our actual integration by parts. So we want to choose u to be, doesn't really matter in this case, but let's choose u to be sine x, and u dash then is going to be cos x, v dash is e to the x, and then v is also e to the x. Okay, let's do our integration by parts now. So it's going to be u times v, so e to the x times sine of x, minus the integral of u dash times v. So again, e to the x cos x dx. Okay, now I need to use integration by parts again for this second integral. So we can choose u to be cos x, and u dash is going to be minus sine x. That means v dash equals e to the x, and v is also equal to e to the x. Now, in the first integral, in our green use of integration by parts, we kind of had a free choice here. We could have chosen u to be e to the x if we wanted to, and v dash to be sine x. However, we chose it to be u equals sine x and v dash equals e to the x. Because of our first choice, that's actually restricting the next choice. We've had to remain consistent throughout here. So what do I mean by that? I chose the trigonometric function to be my u, or the thing that I'm going to differentiate, which means in this, so that was in the first case right here. In the second case, I have to now also choose the trig function to be differentiated. If I chose the exponential function to be differentiated in the second case, then that would lead to a problem. And I'll actually leave that as a bit of an exercise for you to see what would happen. But the idea is that we have to remain consistent in our choice of u. So if we choose u to be the trig function in the first integral, or in the first application of integration by parts, then we also have to choose u to be the trig function in the second application. If we had chosen u to be the exponential function in the first case, then in the second case we have to use or choose u to be the exponential function. Okay, now continuing on with our integral. We still have e to the x sine x sitting here. Now minus the next application of integration by parts, u times v. So cos x times e to the x minus the integral of u dash times v. Now you can see in the u dash we have a negative, so that's going to make this a positive. So we have sine x here and e to the x here. Okay, let's distribute that negative through now. So that gives us e to the x sine x minus e to the x cos x minus this integral. Now what is this integral? This integral is exactly what we started with. We have a recurrence of our original integral. It's popped up again. Now we could write that out again if we wanted to, but we gave it a label. We called it I, and that's why I called it I. Because just in case it pops up again, I don't have to write the whole integral, I can just write the letter I, and that makes sense. So the left-hand side is equal to I, and we also have I on the right-hand side. So if I bring that I over to the left-hand side, I'll get 2i equals e to the x sine x minus e to the x cos x. We can actually factor out e to the x here, so might as well do that. So we get sine x minus cos x in the brackets, which means that I is equal to a half e to the x sine x minus cos x. And then, since this is the end of our integral and it's indefinite, we can add a plus c. And that is our final answer.